In this video, we're computing the arc length of the cardioid r of theta equals 2 plus 2 sine theta. And just so you have a sense for how the thing is graphed, we'll run an animation real quick. So that animation runs from 0 to 2 pi. But it's important to realize that we could start at negative pi over 2 if we wanted. That's where this cusp is. And since the sine of negative pi over 2 is equal to negative 1, this is 2 minus 2, and I get 0. So what I'm going to do is naively set up the arc length integral, but what happens is we run into an issue that requires us to shift to this new starting point of negative pi over 2. So I wanted to get that out of the way first. Now here's a quick reminder of the arc length integral, and I'll post a link real quick to the video where that was derived. So we take r prime and we square it, and we add it to the square of r, and it's inside of a square root. Let's go ahead and prepare ourselves by getting r prime real quick. So r prime is going to be 2 cosine theta. And we'll go ahead and naively assume we can integrate this thing on 0 to 2 pi. And again, I know I'll have to adjust that a little bit later. And when I square r prime, I get 4 cosine squared theta. And then I have to square r itself, which is 2 plus 2 sine theta. So the 2 can be factored out of that. And then it's squared. That gives me a 4. And that means I can pull a 4 out of every single term inside of this radical. And that gives me a 2. So I'll just go ahead and put it out in front. And I'm going to expand that leftover 1 plus sine theta quantity squared. And when I combine the cosine squared and the sine squared, that gives me 1. If I add it to the other one, I end up with 2 plus 2 sine theta inside of the square root. And I'm going to factor a square root of 2 out of that and put it in front. So this is actually a pretty tricky integral. And one way to handle it is to use a conjugate. So we're going to multiply the numerator and denominator by the square root of 1 minus sine theta. And the point of multiplying by a conjugate is always to intentionally build the difference of two squares. When I multiply the interiors of the square roots in this numerator, I get 1 minus sine squared theta. But that simplifies to cosine squared theta. Well, it would be great if we could just call the square root of cosine squared theta cosine theta, because that's the derivative of the interior of that radical piece in the denominator, and I'm set up to do the chain rule backwards. Unfortunately, the square root of the square of a thing is actually its absolute value. It's got to be a positive result. So when the cosine is negative, I can't simply replace this numerator with cosine of theta. There's another issue in here that's popped up. If I integrate from 0 to 2 pi, then when I hit pi over 2, the denominator vanishes. The numerator vanishes as well, but still it's undefined there, and I shouldn't be integrating across points that are undefined. Okay, so this is the point where we have to change our approach with our limits of integration in order to get around some of these issues. So I'm going to switch to just finding half of the area of the cardioid on the interval negative pi over 2 to pi over 2, and then I need to double the results. That gives me a 4 root 2 integral from negative pi over 2 to pi over 2. And then the square root of cosine squared does become just the cosine function now, because the cosine is always positive on that interval. So that issue is fixed. I still have at one of my endpoints a point where the integrand is undefined, but we can handle that formally with a limit now. So I see the derivative of the interior of that square root sitting in the numerator. Just to highlight that, I'll put a minus sign on it. Negative cosine theta is the derivative of 1 minus sine theta. And then I'll compensate with another factor of negative 1 out in front. So now we can just guess the chain rule backwards. And I have 1 minus sine theta to the negative 1/2 sitting right next to its derivative. So I just add 1 to the exponent, and I get 1 minus sine theta to the 1/2. And then I have to divide by 1/2, which is the same as multiplying by 2. And I'm evaluating this from negative pi over 2 to pi over 2. Now when I plug in the upper limit, again, that's a problematic point because the integrand was undefined there. It made the denominator vanish. And so formally, I should deal with that issue by expressing it as a limit. Let me clean up the constants out in front. That's negative 8 root 2. And again, when I plug in my upper limit, instead of just plugging in pi over 2, I really should say it's the limit as theta goes to pi over 2 from the left. 1 minus sine theta to the 1/2. And there's nothing tricky about this limit. If I just sub in theta equals pi over 2, the sine of theta is 1, and I get 0 for this limit. Then I subtract what I get in from plugging in the lower limit of integration. That gives me a negative 1 minus sine of negative pi over 2 to the 1/2. And sine of negative pi over 2 is negative 1. So this piece is 2, and I have a negative 2 to the 1/2, or negative square root of 2 in here. So in the end, I have a negative times a negative, so I get a positive result, which is encouraging because arc length is positive. And I have 8 times root 2 times another root 2, which is the same as 8 times 2, and I arrive at my arc length for the cardioid curve. It turns out to be exactly 16. And we're done. If you find the math content on Zach's Lab helpful, click on the Zach's Lab logo on the right to browse playlists and subscribe to the channel. I produce dozens of new videos per month, and subscribing is the easiest way to find new content. Thanks for watching.